Yes, I once again welcome you the lecture series of microprocessor and microcontrollers. Today is day 9. We are going to discuss the uh, pin description. This is the second class of the pin description. Okay. So now you know that basic structure of the microprocessor: ALU, resistors, timing and control unit. Then we are already completed the memory. It is equally divided RAM and ROM. Okay, it is of 1 MB memory is there. So here the next one is interfacing unit. It has some pins. So how many pins here? 40 pins microprocessor. Out of these 40 pins only, you are connecting memory as well as input output devices at the same time. Some another additional devices like secondary memory and some more number of input output devices by using these 40 pins only. That's why we are using same pins as a multiple purposes. That's what we call it as a multi-purpose lines or multiplex lines. Okay, so you see this you know that microprocessor is a 16-bit microprocessor, you know that. Okay, so microprocessor works in two different modes for single processor mode and multi-processor mode. Or you can also call it as single processor mode as a minimum mode, So multi-processor mode you can also call it as a maximum mode. You see this maximum mode. Okay, so microprocessor works in two different modes. First one is single processor mode, or you can also call it as a minimum mode, or multi-processor mode. You can also call it as a maximum mode. So out of that 40 pins, so for the simplicity purpose, they are dividing into the three different categories. The common signals that are used for both the minimum and maximum modes. Only signals used in minimum modes. Only pins are signals used in the maximum. Now see this. This is the basic structure of the pin diagram of the 8086 microprocessor. This is the so it is operates at the maximum mode as well as the minimum mode. So most of the pins out of these 8 pins, 1 2 3 4 5 6 7 8, so nothing but 31 to the, see this, 31 to the this. Only these 8 pins are different from maximum mode to the minimum mode. So remaining pins, nothing but 32 pins are common for both the minimum and the maximum mode. Only 8 pins, 1 2 3 4 5 6 7 8 pins. 5 6 7 8 pins. These 8 pins are different from the maximum to the minimum. Whenever minimum mode, see this. So 30th pin is hold. In the maximum mode, that pin is RQ bar GT. RQ means a request, GT means a grant. Okay, so likewise S2, S1, S0 in maximum mode, 28th, 27th, 26th pins. But in a minimum mode, that pins you can call it as a M by IO bar, but memory or IO bar, data transfer or receiver, ALE, nothing but this type of the pins. The only 8 pins are different from maximum mode to the minimum mode. Okay, remaining 32 pins are common for both the minimum and the maximum modes. You know that this 8086 microprocessor is available in 3 different clock speeds. You know that whenever you want to buy the microprocessor nowadays, i3 processor, okay, 3.2 gigahertz or 2.0 gigahertz or 3.0 gigahertz. You know that what is this gigahertz? That the gigahertz will indicate the clock speed. If this clock speed increases, the speed of the microprocessor is also increases. This is one of the factor. But in our 8086 microprocessor, the clock speed only 5 megahertz, one version. Another version is the 8 megahertz. Then another version is the 10 megahertz only. 10 megahertz only. But nowadays it is available in minimum of 3.2 gigahertz and all. You know that gigahertz, but it is in the megahertz only. You know, you can identify the speed of the 8086 micro. You know that you can compare the speed of the micro. It is very less speed when compared to nowadays processor. Very slow processors. It consists of 29,000 transistors. In build, it has 29,000 transistors are there. So by placing the 29,000 transistor, we are using technology VLS, a very large scale integrated also. You know that it has 16-bit line, 16-bit data lines and 20-bit address lines. It is sum up of the 1 MB size. So 1 MB memory size is always depends upon the address lines. Always depends upon the address lines. It has more than the 29,000 transistors. 29,000 transistors. Suppose multiplication and division operations also. Okay. Now see this pin description in the last class also we are completed this pins AD0 to AD15 and and A16 to the A19. So you can also consider A16 to the S3, A19 to the S7. You know that. You know that. So these are bidirectional lines. These are AD0 to the AD15 lines. Nothing but A stands for address. Then D stands for data. You know that. See this basic diagram once again. Whenever yes, memory is in the address form. Remember, memory is divided. RAM and ROM memory is divided segments. Each segment it has some address. 101 for suppose 1002, 1003, 1004, 1005, 1006 for suppose we can take. These are the addresses. These are the address locations. Likewise, our house has some addresses. In that house, we are living there. Likewise, so this address has some data. This address has some data. Some data. This address has some data. So this data is 16-bit only, but this address location is 20 bits. Addresses has 20-bit addresses, but in that addresses the data is only of 16. So 2 power 16 is nothing but the how much? How much? It is of 64 KB only. How many addresses are there? 2 power 20 is equal to 1 MB addresses is nothing but 1 MB memory. So nothing but in our 806 microprocessor, 16 logical segments are there. 16 into 64 KB is equal to the 1 MB is there. Like this. So by connecting this one, so these are address lanes. So microprocessor is generated the address. Nothing but one way is okay. But when it comes to the data it requires the two-way, because a microprocessor to the first CPU to the memory can send the data at the same time. Whenever microprocessor is want some data, you get the data from this memory to this. So bidirectional. So we require the data. Remember, data is always a bidirectional lines, but address is always a unidirectional lines. At the same time, multiplex. What is the meaning of multiplex? You know that. But the same pins, you know that pins, you know that pin numbers. What are the pin numbers? 16 to 2. You see this 2 to the 16 pin numbers. At the same time, 39 pin numbers as a multiplex. Nothing but the same pins are used for both addresses. At the same time, the same pins are used for both data. So that's what we call it as a multiplex lines. Multiplex lines. So these are the 16 bits. You know that 16 bit. So 8 bits and 8 bits data. So out of the 16 bit, this is a lower order. This is a higher order. Higher order. Lower order and higher order. So this AD, see this. You see this? Change the pen color. You see this? You see this? AD 8 to 15 is indicates the higher order. Nothing but AD 8 to 15 is the higher order. Then what is the lower order? AD 0 to AD7 is the lower order. You know that out of 16-bit data, we are subdividing into the 18-bit, because we have the AX register, it will divide into the AH and AL. L means a lower order, H means a higher order. Likewise, BX, CX, and DX. So that's why each and microprocessor is considered each 16-bit data into the 8-bit lower order and 8-bit higher order. So 8-bit lower order data is carried by the AD8 to AD0 to 7 lower order data. AD8 to 15 is carried by the higher order. So these are the sometimes. So what are the some another lines is available? A16, A17, A18. These are also the uh, multiplex lines. These are also the multiplex, but unidirectional. Remember, but unidirectional because only one way. Because only one way. You send the information only. You send the information only. Because you will not get the information from memory to that CPU. Unidirectional. Remember, these are the unidirectional. Only one way you can send the information from the CPU to the memory in address. So, but these are the multiplex lines. Multiplex means the same pins we are using for the multiple operations. Nothing but so A19, A18, A17, A16 are the address lines, but S6, S5, S4, and S3 are used for the status lines. These status lines will indicate the status of the microprocessor. Microprocessor is performing which operation. Microprocessor is considering are accessing which segmented memory, whether it is a code segment or whether it is a data segment or whether it is a stack segmented memory or whether it is a extra segmented memory by seeing this status lines. By seeing this status lines, you know that by seeing that S4 and S3 see this. So all the things were completed in the last lesson, but once again we are repeating this. Okay, so when this is a 1 1 series, it can access the data segmented memory. Whether it is a 1 0, it can access the core segmented memory. It is a 0 1, it can access the stack segmented memory. It is 0 0, it can take the alternative but extra segmented memory. Okay. Now the question is, these are the bidirectional. At the series AD0 to 15 are multiplex. AD0 to the 15 at the same time A19 to the A16 are the multiplex lines. But same pins are used for the both the purpose. Then how we will convert one state to the another state? Nothing but address line to the status lines or address lines to the data lines. How we will convert them? So in practically there is a one tri-state buffer is there. Tri-state buffer. Tri-state buffer is there. In between that there is one hardware component is available in this 8086 microprocessor. It can convert this address to the data lines or address to the status lines. In tri-state buffer is available. Okay, that is hardware. But who can give that signal to the tri-state buffer also? So in minimum mode, ALE is on. ALE is enable. ALE address latch enable. In maximum mode, it is QS0. If these pins are on enabled, so these address lines can convert into the status. Here, this address lines is converted to the data. Remember, these lines are always, you know, that straight state buffer. If it is available on a state, then only it can convert into the another state. Okay, it is always available at one state. So nothing but these lines always available at the address lines. But initially these are at the address lines. You want it to convert into the data, or you want it to convert into the status lines. You just enable the address latch enable ALE in minimum mode and the QS0 in the maximum. When these are enabled, so this address lines is converted into the status, or this address lines is converted into the data lines. So once it is on, remember, once this is on ALE, address lines is converted into the data lines 0 to the 15 lines. Then remaining lines A19 to the A16 lines is converted into the status lines like S6, S5, S4, and S. Yes. Now see this BHE, bus high enable. BHE stands for bus high enable. What is this bus high enable? You know that microprocessor. A 16-bit it carries the 16-bit data. 16-bit data. So these are the 8-bit higher order. These are the 8-bit lower. So these is carried by the D0 to D7 data lines. This will be carried by the D18 to D15 data lines. So these are mainly depends upon, as you know, that Registers are responsible for carrying this information. So we have four different types of registers are available. So AX, BX, CX, DX. Again, these are the 16-bit registers. Whenever you want that, the 16-bit registers is converted into the AH and AL, 8-bit and 8-bit higher, 8-bit lower. L stands for lower, H stands for higher. So in the microprocessor, you just given memory to the 8-bit only to the microprocessor. To the microprocessor, you given memory to the 8-bit only. And the time you should know that for suppose the program in the program move AH comma some H 08H nothing but R move PH comma 06H for suppose. This is the data. This data is only of 8-bit data. 8-bit data. So that's why I represent AHRAL. 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 Okay, remember AHRAL. Okay, you understand that. So in that time, whenever you can on this whenever this pin is high, nothing but you know that whenever this pin is represents the bar, you know that a bar, any signal it represents the bar is nothing but for suppose RD bar or the signal BHE bar. That bar is indicates the negative logic. Negative logic. Negative logic means here, what is the negative logic? 0 is on, 1 is off. 0 is set, 1 is reset. A negative logic. What is the positive logic? Positive logic? 1 is on, 0 is off. Nothing but set, 1 is set, 0 is reset. Or this is enable, this is disable. But in negative logic, whenever the any pin or a signal which represents the bar, that indicates the negative logic, nothing but it operates quite opposite way. So nothing but 1 is off and 0 is on. So if this is BHE bar is equal to a 0, I means it's 0, nothing but it is on. It is on. I means it on. Low means here off. Here again the logic here, you know that in STLD and all subjects, you know that very well. I means here negative logic. I means here 0. Low means here 1. Nothing but negative logic, that is. So it is equal to 0. Nothing but on. So on the time, the data is out of this data bus is carry the information by using this D8 to the D50. So okay, so this when uh, this signal is used, whenever where this signal is used, when this signal is helpful, whenever you are connecting the, see this 8-bit input output devices, 8-bit input output device, and the time you can enable this okay. So now see this signal S7 signal, PH bar under this signal. If it is 0 0, now see this, it is 0 1, it can only take the upper byte from the data. So 1 0, it can take the lower byte of the data. 1 1 is none. So I will tell you the next class. There is a physical address is there. On that time you can add the odd address as well as even address. The entire address is also divided into the even 8-bit even and 8-bit odd address. 8-bit even and 8-bit address. The physical memory organization, you will see that. Then we can see the another signal RT bar, read. Remember read. RT bar. RT means read. RT bar. You know that a negative logic. If it is RT bar is nothing but the, if it 0 means here on, 1 means here on. RT bar. So why you are using this signal read? Remember read. A read signal. Or in our terminology, you can also call it as a copy signal. When this signal is helpful, how this signal is helpful to the microprocessor, how this pin is helpful to the microprocessor. Remember, whenever this is the CPU, so this is the memory. Memory has the some data. Memory has the some data. Whenever microprocessors want the data, on the time we send some signal, some address. For suppose this data is available. This data is available. So for this address 1001 address is generated. So microprocessor is coming to this location. This location has some data. Then how this data is come back to the memory to the CPU? How this data is come back to the how this data is back to the memory to the CPU? How this possible? So on that time, this microprocessor is generates some signal called the read signal. Read. You can read the data, nothing but copy that. Whenever you want to study some textbook or something about that, what is the meaning of that one? You read the textbook or you read the material or something like that, nothing but whatever the information in the textbook or whatever it may be, you just memorize it, that one, nothing but you just remember that one. That means here you just copy that information, or that but you read that information, that but the data that is available in the memory is copied from the CPU. You can generate the signal, read. For suppose, when the data is available on the CPU, you send it to the memory. You can see the arrow. You can see the arrow. You can see the arrow. Data is available on the CPU. Send it to the memory. And the time you perform the, for suppose your brain. For suppose you are write the examination. You are write the examination. What we will do? You write the examination, nothing but the paper, it has some information, nothing but likewise only the CPU has the information, send it to the memory. So that time you can implement the write instruction at write pin. Okay, when you read, nothing but you can copy the information. Remember, read means copy, write means send. Okay. Yes, ready. Next instruction is ready. Ready instruction. Ready instruction. A very important one. This ready instruction. Whenever you know that, you see that once again the basic structure of the microprocessor. Clear all this. You can see this. And input-output devices. For suppose you are connected input-output devices at the same time memory to the CPU. What is the speed of that CPU? 5 megahertz, 8 megahertz. Clock speed, remember 10 megahertz. Then what about the speed of this input output devices memory? You know the pen drive speed. You know, for suppose you are connected to the pen drive input output device to this CPU. You know the pen drive speed. It matches the CPU speed. No, it cannot matches the CPU speed. Okay, our memory, this memory speed also cannot matches the CPU speed of that memory. CPU speed cannot matches the CPU speed. So it nothing but the speed. Time in controlling speed, it cannot matches them. And that time when you match the uh, speed of the input output devices as well as the CPU speed. CPU speed. You use the as you know that and interfacing devices. Interfacing devices. You know that interfacing devices 8255 PPI. So one of the advantage, one of the requirement to add these peripheral devices to the CPU is to match the speed or match the compatibility and all. So one of the compatibility is a speed. Speed. You remember here in this case we are considering the speed. Speed. So the speed is very much higher when compared to the this one. So on the time, you see this on the time. On that time. So remember once again one another example. For suppose a computer connected to the printer. Connected to the printer. You send the printer, some computer to the printer, some print the some 100 pages. Printer speed is always slower when compared to the computer. Remember, always slower. So what it can do here is, so this printer is ready to print the pages. This information is printer is send the information to the CPU. I am ready to print because for suppose you are printing. Suppose you are giving the 100 printer to the command print the 100 pages. So without replying the printer and information to the computer, what information I am ready to the print, it can nothing but acknowledge that one. It can acknowledge that one information. So the printer is acknowledged to the computer. I am ready to the print the pages whatever given by the computer. Okay, on that time only, on that time only, on that time only. Okay, the computer is send the information to print the data. So that information I am ready to print the information or I am ready to work that one, that acknowledgement is that given by the slow memory devices as well as IO devices. That acknowledgement is given to the microprocessor by using the array set. Nothing but a reset. You know that reset signal, a system reset signal. You know that whenever you press this signal, it comes to the uh, uh, nothing but the initial state of that signal. It is active I. It is nothing but active I means one. Okay, so nothing but now you know that reset. You know that your cell phone also you are performing the reset operations, or you are some additional some devices like some memory devices. You press the reset signal, so it comes to the initial state, starting state almost. Whenever it can perform any operation also on that time when you press the reset, that operation is terminated and coming back to the initial state. This is the use of the reset signal. Next one is the interrupt signal. Interrupt. INTR, interrupt request signal. Interrupt and request signal. So as I said in the in the first class and second class, I said if the number of pins of the microprocessor is increases, the performance is also increases. But at the same time, if any of the microprocessor, the performance, the efficiency, the robustness is depends upon the interrupts. If more number of interrupts, it's like a more powerful microprocessor. What is the meaning of this interrupts? Again, coming to the computer, the printer. Our printer comes scanning Xerox machine. So you given some command to the printer, can print the 100 pages. So it is printed. So printing is going some 40 pages is printed. On that time, you can send the another signal from the computer to the printer. You can stop the that 100 pages. Then print the another document to for suppose. On that time, you send us some interrupt request to that printer. If it is acknowledged that one, then it can print the another whatever the information. For suppose you are printing 100 pages, some another person is coming to you and no, I want the urgently print this 20 pages, some document to 20 pages. So on that time you can stop that processes, and that one can interrupt that processes and given commands to the printer to print the another second document. So on that time, so you can interrupt the current operation. You are going to interrupt that operation. You must give in the some interrupt request to that. So the next one, a non-maskable interrupt signal. So interrupts are two types. Interrupts are two types: maskable, non-maskable. Maskable means whenever you write the programming to change the operation or for the but it is not possible. Not possible. Interrupts are two types: maskable interrupts and the non-maskable interrupts. For suppose, how for a best example for this one is, for suppose you are playing a game in our cell phone. A message is a WhatsApp message or company message or general message is coming to you. What will happen if that game is paused? No, it is not at all paused. It can shows the some notification, so you got some messages like that. That is also interrupt. That is programmable interrupt. That is maskable interrupt. You are off that notifications. That one is also not showing that. But whenever you are playing the game, your friend is called to you. On that time, the game is interrupted, so it shows the call. Yes, that is the non-maskable. So every microprocessor or every system, it has some non-maskable interrupts. And you are not at all changing that functionalities. Okay, without writing the with any without any changes. You are not changes that one by writing the program or like that. So likewise only. So for suppose when you start the microprocessor, it is starting that one. So like with some programs, it is already fixed in the memory location. You are writing the program also, you are not changing that. That we can call it as maskable, non-maskable interrupts. Non-maskable interrupts. Okay, then uh, another type of the pin is test. A test signal is there. What is the test? What is the test signal? The test is nothing but whenever you want to connect the processor, some one processor to the another processor. You see this, you see this, you match the processor for suppose of 8086 or 8087 processor. So on that time, whenever it is 0, it can acknowledge that one. Okay, so it can wait to connect the another devices. Okay, a very simple signal. This is the clock, very important. You know that clock, you know that clock. 5 megahertz clock, 8 megahertz clock, you have 10 megahertz clocks are a clock is available outside of the microprocessor. Outside of the it is a quartz crystal oscillator. A quartz crystal oscillator. It is available outside of the microprocessor. Okay, so one terminal is connected to the this pin 19, that we can call it as a clock. You can supply this quartz crystal oscillator is continuously supplying clocks to this microprocessor. But different operations will require the a different number of clocks. You see this? You see this once again. This one timing and control unit. What is this timing and control unit done? It can send these some different clocks to that each and every devices to activate the different number of clocks. I said in the previous classes, you spend the one class on this timing and control unit. This timing and control unit is connected to the each and every component present in the CPU at the same time. Outer side of the CPU, nothing memory as well as input output devices. So it can control that one also. It can control that. How it can be controlled? It can send us some fixed number of clocks for that operation. For suppose when you perform the read operation, it can send the 4 clocks. It can perform the write operation. At the same time, it can also perform the gives the 4 clocks. Likewise, like that. So it can whenever that when so it can send some fixed number of clocks to that any of the input output devices as well as memory to activate that one, to control that one within the CPU as well as outer side of the CPU. But so the CPU, then who can supply these clocks? A quartz crystal oscillator is supplying the clocks, the 5 megahertz, 8 megahertz, 10 megahertz. That depends on the versions. So this watch tester oscillator is continuously supplying the clocks. Remember, continuously supplying the clocks. But as you know that for read operation you require the 4 clocks, for write operation you require the 4 clocks and like that. So who can divide that number of clocks? That is divided and that is aggregated by using the timing and control. Okay. The next one. The next signal, VCC and ground. You know that VCC, VCC and VSS. VCC is the pin power supply. VSS is the ground. The two pins are dedicated for this one. This one VCC is nothing but you can give in the power supply nothing but in 8086 microprocessor. How many volts of the power supply you are given? You are giving the 5 volts DC plus 5 volts DC plus 5 volts DC. Okay, 5 volts DC. So yes, now coming to the next one. Whenever you want to, like as I said, microprocessor, the pins, whatever you are discussing, these pins, what are the pins here? AD0 to the 15, A19 to the A16 status pins, as well as BHA pins, as well as read and read, write, enter, NMI, clock, and VSS, whatever it may be. These 32 pins are for both minimum and max. But these 8 pins are different for maximum mode to the minimum. Now we are going to discuss that one. So how this microprocessors convert one state to the another state, minimum state to the maximum state, or maximum state to the minimum state. So that purpose we are using this MN expert. If it is equal to the 1, it will work as a minimum mode. If it is equal to 0, it will work as a maximum mode. So nothing but 1 is nothing but I, or it is nothing but set or enable. Different names are there. If it is 0, is nothing but reset or disable, whatever it may be. If it is equal to 1, high, nothing but minimum. It is equal to 0, coming to the maximum, nothing but low. High and low can also called as low. So if Mn or Mn slash Mx bar is equal to 1, it will work as a minimum mode. Mn slash Mx bar is equal to 0, it works as a maximum. So for that purpose, we are using this pin. That pins. So now see this pins 34 to the see minimum mode. These pins are the maximum mode. Remember, these pins are the maximum mode pins. So now see this minimum mode pins INTA, interrupt acknowledgement signal. Interrupt acknowledgement signal. You know that for the printer and computer operations, so you will print the 100 pages, but you stop that 100 pages and print the another document. On that time, you send the request to the computer to the printer. You just interrupt that one. On that time you can generate the interrupt request signal. So when that request is accepted by that printer, on that time it can send the interrupt acknowledgement signal. So I am ready to stop that process and print the another pages. Likewise, I am telling you some example. So interrupt acknowledgement signal. That purpose we are using this interrupt acknowledgement signals. You know that what is ALE address latch enable? What is the meaning of the what is the use of this address latch enable? This lines, you see these lines. These lines, you see this lines is always in the address state. Whenever you want to convert this address to the data as well as data, in this mode we can enable the ALE. Okay, and the time this address lines is converted into the data lines. DEN signal, data enable signal. So this signal is used to using the data transfer and receiver operations. You know, see this in the trans receiver is used to separate the data from the address and the data buses. Okay, this is active low signal. The signal is used to enable the data enable the. Now see this. Best example, address data. It is always in the address state. Lines are always in address state. This state to were converted into the data bus. Data bus. But you can by using the ALE. You just only enable that one. This pin to the this state to the state by using the tri-state buffer. Remember, tri-state buffers are available to change the state of these pins addressed to the data. Once this operation is completed, remember, this data lines again convert to the address lines. Once this operation is completed, whatever the information you get the data from the memory to the CPU or from CPU to the that operation is completed, that instruction is executed. Once then again it is converted into the address buses. Now it can carry the data. ALE is only enable the address to the data, but it carries the data. That time it can enable the this DEN. Okay, signal. So data transmit and the request DT by R bar. Remember, it is equal to the one data transmission. If it is equal to the 0 receive. Remember why it is receive bar, nothing but bar is indicates the 0 is on bar. When it is dt is equal to the 1, it is data transmission and data receive. Where it can be used in the data transmission and data receive. Data receive. You know that you are converted the or you are connected the some memory, some pen drive or USB to the computer. We can you are using the device user in this one, USART in this one. Universal synchronous asynchronous receive and transmit device is there in between the interfacing device in between the computer as well as USB. Whenever you want to send the information from computer to the USB or USB to the computer, it send the signal to that USB. I am ready to send the information and R. So on the time it can send the signal DT, data transmission signal. Okay, or whenever the information is USB, you get that information from USB to the computer. On the time you can send the signal and receive signal. So on that way, when the signal is 1, you know that so data is transmitting from computer to the USB. Or when the signal is equal to 0, you know that data is received from input output devices or some another memory device to the receiver. For that purpose, this signal is used. So memory by IO bar signal, a very important M by. Then coming to the this diagram also just for a second. M by IO bar. You see this. You see this. Okay, you see this. So AD 0 to AD 15 lines were connected. This one memory. A19 to the A16 lines were connected at the same time. How to access the input out? For suppose we are connected the USB or external hard disk or some keyboard or something about it. How to connect this CPU to the input output devices? That will be connected by the AD0 to the AD15 lines only. AD0 to the AD15 lines. It is connected by this lines. Okay. Input output device data is 20-bit. Sorry, 16-bit only. But memory device address is 20 bits. Remember. So for suppose microprocessor M by IO bar means whenever microprocessor want to connect to the memory, on that time it is equal to the 1. Or whenever microprocessor want to connect the CPU is wanted to connect the input output devices, on that time it is going to the 0. 0 means a input output devices, 1 means a memory device. Yes, this is the CPU. CPU is want to connect the memory. And the time this pin is equal to the 1. Nothing but CPU is directly connected to this memory. But when that pin is equal to the 0, you write the some instruction, in and out instruction. And the time microprocessors know that you are going to connect the input output devices. Remember, otherwise it is always this pin is equal to the 1. Remember, whenever you are in the instruction in the programming, you are right in and out instruction. In means your input device, out means your output device. In that time only microprocessors know that, so we are working with the input output devices. And that time this I m by io bar pin is equal to the 0. And that time CPU is connected to the input output device. Otherwise it is always is equal to the 1. So that is always connected to the memory. Okay, always connected to the IO. Uh, just only two signals are there. Remember, yes, right signal is also there. You know that right signal. What is the meaning of right signal? Whenever the data is in the memory, you want the data to the CPU, and that time you can perform the write operation. So, sorry, I mistaken that. That is a read operation. What is the meaning of write operation? Whenever the data is in the CPU, whenever you want to send the data to the memory, you perform the write operation. Nothing but send information. Read means here. What is the meaning of read means here? Copy the information. Nothing but from memory to the CPU. But write information. Write an exam. Write an exam. You write the exam means your information is in your brain. So you put it on the paper. Nothing but writing. Writing. That is the writing. That write means the information is in the CPU, that is sent to the memory. You can perform the write instruction. Where it is equal to the 0, so you can perform the write operation. Then hold acknowledgement signal. Hold and HLDA means here hold acknowledgement. HOLD means here hold. So the signal is used in the DMA, direct memory access control. And one another concept is there, DMA memory, direct memory access. And that time, whenever microprocessors want to uh, access this DMA, it can send a signal called hold signal. So this DMA is ready to get the information from the CPU. On that time, it can acknowledge the HLDA, that will indicate the hold acknowledgement signals. Hold and hold acknowledgement signals. These are mainly used for the DMA. DMA means here direct memory access controller. And that this is very simple. Very simple. CPU, you can access the DMA. It send the information hold. You can see the arrow. If it is DMA is accepted that request or that one, you can send the HLDA hold acknowledgement. So I'm ready to take it. That is. So in the next class, we are going to discuss the maximum mode. Thank you. Thank you for joining the session.